Tekrar hoş geldiniz hepiniz. Bugün mühendislik ve analiz konularında hizmet veren Simofis ve Navis mühendisliğinin işbirliğiyle düzenlediğimiz webinarın konusu model tabanlı simülasyon yazılımı Amesim ile iklimlendirme. Bugün Siemens'ten bize David Jimenez eşlik edecek. Kendisi bir sunum yapacak, arayüzden gösterimler yapacak. Webinarımız kayıt altına alınacaktır. Dolayısıyla soruları en son kaydı kestiğimizde alacağız. Welcome everyone. The topic of our webinar is HVAC systems with 1D simulation software Simcenter Amesim. David Jimenez from Siemens will be our speaker today. Our webinar will be recorded. We will take the questions at the end of the webinar. Now let me leave the stage to David.
Good afternoon, everyone. Thank you very much, Ali, for presenting myself. I'm going to share my screen. Super. Can you see my screen?
Yes, all clear.
Super. Very good. Super. So welcome, everyone. And first of all, thank you for being here. I'm David Jimenez. I'm pre-sales solution consultant, focused for system simulation, focus for Simcenter Amesim, and I'm here to present the added values of Simcenter for railway industry. So if we talk about the different drivers of industry, first of all, one of the main topics nowadays are green and clean power. So for that, we are talking about propulsion system, diesel, internal combustion engines, how we electrify more and more the train systems, how we integrate new systems, as for example fuel cell system, how can be integrated in the global system. As well, we can talk about passenger comfort, or for example, where we take into account vibration, but as well, for example, the thermal comfort. We can take into account as well safety, for example, or performance of the train system. So for all of that, we strongly believe that system simulation and this tool Simcenter Amesim, thanks to their mechatronic capabilities, we can propose added values. We can propose we can help the different customers, to get new systems faster in the market, fulfilling all your requirements. So for that, we have done 3 series of webinars where we explain those points, how Amsim can be applied for railway industry, for mechanical simulation, for electric powertrain, for example, talking about batteries integration, fuel cell integration, and today we are going to focus more on the thermal part, on the HVAC system. So first of all, we talk about system simulation, and we should talk about Simcenter. So Simcenter is the portfolio that we propose in Siemens, where you can find a wide range of simulation tools, where you can find mechanical simulation to do finite elements simulation, as well computational fluid dynamic simulation, for example, with Star CCM, and today, etc., etc. And today, we are going to talk about our offer in Simcenter in terms of system simulation. So the idea is that if we take a look at the V-cycle, Simcenter Amesim system simulation propose bring an added value from the very beginning of the V-cycle, where prototyping start to be built. You start to think and to design a prototype for the future system, and at that point, you start to need some simulation activities. And at this part of this V-cycle, Amsim can already help the engineer to do that thanks to their already mechatronic platform, as well as the ready-to-use physical components available in Amsim. But the idea is that we can go step by step with the customer, with the user, to make more complex the system, and the idea is to get more and more accurate results. Until the fact that you can couple system simulation with CFD, for example, with 3D CA tools. And this is another added value of Simcenter Amesim. Another point that is quite useful as well for companies when we talk about simulation is the fact that we have something called Web App Server, and it's a new tool from some years ago that we propose, where once your Amsim model, your system simulation model has already been done, it's not going to be stocked in one department, and only the expert engineer is going to use Amsim to that model. But you can deploy the system simulation model to all the company, thanks to a web app server that we propose, and we are going to take a look at the end of this webinar. So if we take a look at what Amsim is, Amsim is a tool, as I said, that brings added values from the pre-design phase. It helps for do system sizing analysis and integration analysis. And the fact that we can couple different physics at the same time, it's bring an added value in terms of integration capabilities. We have something quite important to say is that we have a huge number of libraries with already physical components already off the shelf. You have just to drag and drop in the sketch, and it can be used. In terms of physical models, we propose more than 6,500 models and are split it up in different physics: hydraulic, pneumatic, thermal, electric, mechanical, and signal. So if we take into account or take a look at the different systems that are related to the thermal aspect of a train system, we can take a look at the thermal control, for example, or heating, ventilation, and air conditioning. But before starting to take a look at the solution that we propose to do this kind of analysis, I would like to take a look at the integration capabilities of Amsim. The fact that thanks to Amsim, you can cover very specific topics. For example, thermal topic, battery integration topic, fuel cell integration topic. But as well, one of the big added value is the fact that from the very beginning, you can start to analyze any system in an integration way. In this case, for example, I'm showing an example of system of systems where we are coupling different systems of a train. For example, in this part, we are modeling the driver and the vehicle. Here we are modeling the high voltage propulsion and the low voltage board net. Okay, we have the electrical system, but however, the electrical system is generating heat. So for that, we need to model, if we want to take into account how needs to be handled that heat generated by those systems, here we are modeling the thermal part of the electrical system, but as well the cooling system, hydraulic cooling system, that is cooling down the system, the electrical system. And all of that is taken into account in only one tool, Simcenter Amesim. So one example of that integration approach is done by Voith in Germany, where they are using this kind of approach, full vehicle simulation from power source to main consumers. And the idea is that thanks to Amsim, they study the interaction and the behavior of the different equipments on the thermodynamic, mechanical, hydraulic, and electrical domain. And the idea is that they investigate to do energy optimization of the main consumers. So this is just to get an overview of, first of all, the integration capabilities of Amsim. And then what I propose you is to go to the first part of our thermal, one of the thermal topic, that is the thermal control. So in this case, we are going to see some examples in Amsim, but first of all, I wanted to present for this kind of analysis, we use thermal libraries that allow us to model the different heat exchangers that we are going to have in a cabin, for example, and take into account as well the temperature variation as a function of the time. So the idea is that we can do assess of thermal performance, predict air temperature and humidity of the cabin, predict, for example, heat losses from the outside of the cabin, and something quite important, for example, what is the human comfort, how we can assess it. So first of all, I'm going to jump to Amsim, and we are going to take this example to see together what Amsim looks like. So this is Amsim. So first of all, just to take a look at the different, this is the sketch where you can just drag and drop the different components. Here, these are all the libraries already ready to use off the shelf. You have just to take one library and pick up the component that you need to model your system and connect it each other. And then once the model has been connected, all the different components, you can take a look at the different parameters that are related to the equations that are behind. Okay. In terms of equations, there is, for every component, there is the documentation in the help where you can find all the equations that has been used to model that component. So the idea of this model is that we have modeled the different walls of a cabin and the different heat exchangers that are happening in the cabin. For example, the heat exchanger that we are having in the roof, for example, what is the temperature at each wall, for example, and we are modeling the average temperature in the room thanks to our 1D approach. Then the added value of this component of this model is that you can use this model to size, to get a first overview of what is the needs in terms of air conditioning. What is, for example, the volumetric flow rate and the temperature that you need in order to get the objective of the temperature of the room. For example, here we have an objective of 20 degrees, and we are going to take a look, for example, if we inject 420 meter square per hour to the system and to see if this fulfill your needs or not. So we are going to run the simulation, and during the simulation has just finished, so we have simulated 10,000 seconds in less than 0.3 seconds, quite fast. And just before getting the results, something that I didn't mention as well is the fact that here in this part of the model, we are modeling the different properties in terms of material, but as well the solar irradiation that can be used. It's a way to model how the sun is going to affect to your system. It can be used, for example, if you are modeling a room, for example, you can select the city where you are placed or even the GPS location. and even the start date in order to model the variation of the sun. But as well, we can use the user-defined approach where we can use tables in order to modify, for example, if it's not a room, but it's something that is moving. It's something that we can model it as well in Amsim to take into account the movement of the train. Then, so in this case, we have run the simulation, and we can take a look at, for example, the temperature of the average temperature of the room. So what we are doing here is we have no volumetric flow rate at the very beginning. So then there is heat exchanges between the ambient, let's say, and at some point we start to inject some air at a specific temperature, and then we have the cool down to get a stabilized temperature on the room. My temperature objective is 20 degrees. And what we see here, for example, is that I'm going to change of color to, this is my objective. And what we see, for example, is that taking into account the volumetric flow rate that we are estimating, we have a lower temperature than the objective that we were expected. It was 20 degrees. So we can analyze, do batches in order to understand, to calculate what is the best volumetric flow rate needed for that need, for that requirement. And then as well, we can, for example, take a look at the relative humidity. So here, for example, we see that we have, at the end of the simulation, we have 23% of relative humidity. And something that can be interested is what is the PMV. So what is the feeling in terms of temperature and humidity for the user? So we have a sensor here that can calculate the PMV value, and we have even an app where it shows where you are placed, if you are inside the thermal comfort or not. So all of that can be used using Amsim and their capabilities. Here, for example, we are modeling some heat exchangers with, and we are using a specific velocity of the train. We are saying that the velocity of the train, once the air conditioning is start, the velocity of the train is 11 meters per second. But for example, we can take a look if we want to create a mission to say that the velocity, the train will stop, will start again with a different velocity. So it's something that I'm going to change here. I'm going to change of parameter and run the simulation. And what we are going to see is a cycle where the velocity start to change during the simulation. So we had 11 seconds for one specific duration, then we stop again, and then we get higher velocity, 25 meters per second. And then what we see here, if we take a look only at the temperature, is that the temperature that we are getting at higher velocity is lower than before. Why? Because the heat exchangers that we are having, for example, with outside will influence, for example, the calculations. So the idea of this model is to show how from very simple models you can step by step getting more, answering more questions. Okay, I was trying to figure out what is my requirement in terms of power for my air conditioning system for one specific speed, but what happens if I do a mission? So I can get some answers thanks to Amsim. So this is the idea of this plot. Thanks to Amsim, we have already done a thermal analysis of the train. We can go to the second topic. That means, okay, we know the need in terms of power for the heat for the air conditioning system. Let's be in the role of an engineer who are developing an air conditioning system, for example. So we can go to another solution, another verticality that we propose in Simcenter Amesim related to thermal part. And first of all what I'm going to present is based on our advanced fluid description database that we propose in Amsim. So if we talk about fluids, we talk about gas, liquid, and two-phase flow. For each type of fluid, we have different assumptions ready to use. For example, for gas, we propose perfect, semi-perfect assumptions, real gas assumptions, humidity handling, how the humidity will evolve during the simulation time. As well, if we take into account, for example, the two-phase flow, we have different equations of states. The one that are using nowadays our engineers, for example, MBWR, Helmholtz, ECS, and all of these database are validated, for example, with NIST. That is what we believe that is the best reference in the nowadays. So thanks to the database and the libraries that we propose to develop the different thermal systems, we can cover, as for example, these different examples: air cycle example, a steam cycle, heat pump, and all of that, for example, comes from our demo portal. So our demo portal is one page where you have a huge number of ready-to-use models, as the 3 ones that I'm showing, where you can download it and just use it to see some examples, or even reuse that model for your application. Okay. Then I'm going to jump up to another model, and the second model will be an air conditioning model. So here we are using two-phase flow library, and the database, the fluid that we are using is the R410A refrigerant, but it can be possible to change it thanks to our database. We can take a look at the different equation state that we propose. And the idea is that with this model, we are modeling the global thermodynamic cycle of the air conditioning. What we have here, for example, is the heat exchanger that is cooling down the air that is going to the room in order to cool down the cabin room. So here we have the heat exchanger that goes in this direction. And then we have the compressor. The compressor that is compressing the fluid and goes to a second heat exchanger that is cooling down the fluid and goes through an expander. So some analysis that we can do. For example, if we take a look at the temperature after the heat exchanger, we can take a look at is 18 degrees. We know that after the compressor, the fluid is going to be pressed, the pressure is going to increase. So we expect as well an increase of temperature. And then because of the second heat exchanger, we are going to have a decrease of the temperature. And because of the expander valve, at the end, we are going to have the lowest temperature before getting the second heat exchanger, 12 degrees. So here is some analysis that you can find in Amsim. Another point that could be interesting, for example, if you are modeling air conditioning systems, is, for example, the gas mass fraction. What is the gas mass fraction? Is pure fluid, pure liquid, pure gas, or is a mix between both of them? So this we can take a look. For example, if we this are all the variables that it's proposed and you can analyze, and we have something called gas mass fraction, where if it's 1 is pure gas, if it's 0 is liquid, if it's between 1 and 0 is a mixed between both of them. So what we can see, for example, is that going in this direction, as it's heating up, the gas mass fraction at the end, it will be 1. That means that it's pure gas. But if we take into account, for example, if we take a look at the gas mass fraction after the second heat exchanger, we see that from gas is coming back again to liquids as the gas mass fraction is 0. Analysis variables information that you can get a deeper view of what physically what is happening in your system. Okay, and another thing that can be interesting is that we have the two-phase flow air conditioning system, and we have control system that is included in the model. And this is controlling, for example, in this case, is controlling the section of the expander valve. We have an objective. We have an objective in terms of subcooling temperature before the compressor. And what we are doing here is we are adding a sensor, virtual sensor. We are comparing the error, and we are sending that error to a PID that is going to compute which is the best section to what is the fittest section to define on this valve in order to be fully open, fully closed, etc., etc. So here we can take a look at the thermodynamic aspect, the control system. Another interesting point is that if we come back to the thermal aspect of this model, we were taking into account the different variables as a function of the time. But we can define new plots in order to understand better what is happening in my system. For example, we can use our plot capabilities, thermodynamic plot capabilities, and we can say, okay, I want to create a thermodynamic plot. And I have here in the simulation my the thermodynamic plot, and you can see how it's going to evolve as a function of the time. So here, for example, I'm taking a look at how it's changing the temperature and the gas mass fraction, and at the same time, I see how these move as well at the same time in a synchronous way. So the main idea here is you are the expert on developing thermal models for your specific system. Here, what we propose in Amsim is all the tools that allow you as an engineer to better understand what is happening and understand it in a very fast way, let's say, because all the tools are available for you. Then we were talking about the first model where we have the cabin of the thermal model of the cabin. We have the air conditioning model, and then we can have a model where we do the integration. So here we have the cabin thermal model, and we have the air conditioning model, and we integrated both of them in the same model. So as you see, we can go step by step, where first of all, you focus on one system, another system, and at some point you can couple it to analyze the integration of the model. So it's things that can be done thanks to the fact that every library are compatible each other. And so the idea here is that the approach that we were following, and as I explained at the very beginning, is that we were using a 1D approach to model the thermal part of the cabin. So we were modeling the different walls, and the temperature of the cabin, we were modeling an average temperature of the cabin. But for example, we are not taking into account the different 3D phenomena, as for example, the streamline, how the velocity, how is the flow distribution once it's going out from the air conditioning. So for that, I want as well to talk about how us as Simcenter in Simcenter portfolio, how we break the the walls between 1D and 3D. In our portfolio, we propose CFD tools as, for example, StarCCM. And the work that we are doing from some years ago is try to couple as much as possible both tools in order to bring you as a customer and a only solution. So here in the V cycle, you should go step by step, putting more complexity to your system because you need more and more accuracy, because the idea is to spend less real tests, because the simulation will bring the information that you need. And at some point, 3D start to be more and more needed until the end where you only need a 3D CFD tool, for example, to get the performance of your model. But at some point, there is a need to couple 1D with 3D. If you have the detailed geometry, we can do co-simulation between StarCCM and Amsim, for example. There are one point where, for example, you don't have the geometry of your room, for example, but you want to estimate what is the 3D behavior. And for that, we have developed a new tool called Embedded CFD that we integrate the capabilities of StarCCM in Amsim. And then we do a parametric simplified geometry. And using that simplified geometry, we mesh it, and then we couple 1D and 3D in the same simulation. One of the interesting points of the embedded CFD is what we call a smart coupling. What we call a smart coupling is because we don't run a co-simulation every time frequency, let's say every 0.1 second, for example. We manage to be sure that we launch a co-simulation that we call, for example, the CFD tool whenever we need. That means, in this case, for example, the Amsim cabin, its modeling is calculating the mass flow rate and the temperature, the wall temperature that is sending to the StarCCM, and then StarCCM is computing the air mass flow rate between zones and the wall heat transfer, the HTC. So we define some criteria to call the CFD in order to reduce the CPU time. And we say, for example, one of the criteria is, okay, if the air mass flow rate is not evolves more than a certain value, for example, 0.1 kilogram per second, I'm not going to call the CFD tool because the results, the 3D phenomena, will be enough accurate for my needs. But if the mass flow rate starts to change, I will call the CFD in order to refresh the 3D phenomena, the 3D results, in order to have more accurate results in terms of simulation. And it's what I'm going to show here in my third model. So here we have my model where we have the thermal part, the air conditioning part, and the coupling between CFD and 1D. It's done by a component, portless icon component that is included in this sketch. And then the idea is that there is a tool behind this component, and the idea is that first of all you generate your geometry, and I'm going to show. The geometry that we have is a basic one using a basic approach. Then the second part is create the mesh, define the different variables that is going to be coupled between Amsim and StarCCM, and then run the simulation. So here we have different parameters for the CFD setting. And once it's done, for example, this simulation took me 10 minutes. And so it's the kind of approach that we propose is still low in terms of CPU time. We are coupling 1D and CFD with this smart coupling where we get really good performance in terms of CPU time, and we can get an overview of what is happening in terms of 3D effects. And all this information, here we have the visualization in terms of 3D, but all this information is sending to Amsim in order to finish correctly the simulation with the right results from the 3D part. Okay, so this is what we have for StarCCM and Amsim. We bring all the capabilities of StarCCM to Amsim, and this is why we can go step by step with the customer from very simple models to more complex one until get a co-simulation with 3D tools, as I have shown before. So the last point that I wanted to focus on, it's on Web App Server. So okay, imagine that you as an engineer have one of your team, an engineer team, for example, have developed an Amsim model in order to size step by step the system, and then the system has been validated, and that Amsim model, what do you think? Do you think that is not used anymore? That the cycle, the design phase has been closed, has been finished, but there is a second, let's say, life of that model, and is during the operation phase, let's say, and as well as this on the selling process, for example, to sell that to other customers, thanks to Web App Server. So Web App Server is a quite interesting tool because the idea is this, for example, is the different, let's say, experts that we are going to have in the different people that we have in a company, for example. And here, for example, we have our expert on system simulation that are, in terms of number of people in the company, is lower than, for example, that you can have in terms of sales, for example. That the idea is that thanks to Web App Server, the number of users that can take advantage of the Amsim model, it could be quite huge. For example, here we have 10 experts on Amsim, for example, in this case, and for 10 experts, we will be able to, thanks to Web App Server, 100 project engineers, for example, will use Amsim models with no expertise of Amsim, with no knowledge of Amsim, but thanks to our web-based approach, they can create and simulate models to get the result that they need. And for that, I'm going to, and another just a slide before going to one example is, for example, this engineer that is developing one Amsim model, for example, of the thermal cabin. And once he's finished the model, he push it in the server, in the Web App Server, and you will have a good number of people, for example, sales, that will be able to simulate models, for example, to get the right configuration for their customers. And then they can, for example, the salespeople with a tablet or a cell phone, for example, do the configuration of with the customer or a prospect, and create the configuration, simulate the behavior, and show the result with the customer, saying, look at this air conditioning, for example, or heat pump that cover or solve the requirements that you need for your train, for example. So what I'm going to do is I'm going to go to Web App Server. Here I have my my account. And then what I'm going to do is I have a model of HVAC. The application it's for an office floor, but the idea is the same, is that I'm going to go to my project. And here I have some parameters. So here there is no Amsim is behind, but what I I have here is only a few parameters that I can change. So, for example, I start to talk with somebody who are looking for an air conditioning, and okay, I can do some simulation, some proposal, for example, give some information in terms of performance for their need. For example, I have someone who wants to have a temperature in his room of 20 degrees. So I have 30 people. Let's say I have 35 people in my company, and then once I change some parameters, I can simulate. So this is using Amsim behind the scene, but there is no need of Amsim installation. You only need to have access to web app, to internet, let's say. And then once I will get the simulation finished, I will get all the variables that are representative for my system. So in this case, let's wait to run the simulation. We are running a simulation of a whole day. Okay, so here we can take a look at, for example, the people comfort during the office hours, or for example, what is the energy consumption. We can take a look, for example, at the results. Here, for example, are the ambient, in yellow is the ambient external temperature. So here is the night, and at some point the temperature starts to increase. And we see here, for example, the HVAC temperature, the office temperature, and as well the humidity. So here, for example, we can take a look at the different parameters, and you can show that to the prospect. And even if you are you have a role where you are not an expert on simulation, you are even no care, let's say, don't care about simulation, for example, this is a way to deploy, let's say, as a for example, an IT person will see this tool as a way to explode in the best way a simulation model that was done by one of our experts, for example, the expert of Simcenter Amesim. This will be one guy who are using the Amsim model to size, for example, any system, but pushing it to web app server, he get access to a lot of more people in the company to use simulation in their daily based. So just to sum up, as a conclusion, we have talked about Simcenter Amesim, how from with Amsim you can go step by step to go from simple to more complex models, even to doing some couplings between Amsim and StarCCM, and how after, once the model has been done, how can be deployed in a company, in the company, using web app server where no simulation skills are needed. Then we, in this webinar, we focus on the thermal management, and our solution for thermal management are quite good in terms of design, size, validate components, subsystems, assess the impact of different changes in terms of architecture, for example. Thanks to the pre-processing and post-processing tool that we propose in Amsim, helps to ramp up and to speed up the system models. So thank you very much for being here, and yeah, that's all for me. And if you have any question, feel free to ask it, and I'm here to answer all.